there is some unique properties of the problems we're solving. For example, our stack relies on really powerful spatial awareness of everything going on around you, but then you need to understand the world in 3D even better. Another thing you want to incorporate is very long memory over a scene. You need to reason often based on the history of several seconds or more. That can be a lot of frames. You need to think how to prevent hallucinations. So all of this, are still areas that are very much ripe for further work, even though we have these vision language models.
All right, everyone. Welcome to another episode of the TWIML AI podcast. I am, of course, your host, Sam Charrington. Today, I'm joined by Drago Anguelov. Drago is VP and Head of Research at Waymo. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Drago, welcome back to the podcast.
Thank you. Pleasure to be back.
I'm really looking forward to digging into our conversation. I went back and checked. It's been 4 years and a month since we last spoke. It was February 2021, and I have got to imagine a ton has been happening on your end. So I'm really looking forward to catching up on all that. We'll be especially digging into some of the work that you've been doing to incorporate foundation models and that whole idea into the self-driving experience at Waymo. But before we get going, I'd love to have you jump in and share a little bit about your background for folks who weren't listening 4 years ago.
So, a lot has happened in the last 4 years. I'm Drago. I've been at Waymo for almost 7 years now. I have been leading the Waymo research team since summer of 2018, and we focus on pushing the state of the art in autonomous driving systems with machine learning or AI, or both. And I have been a machine learning researcher for over 20 years. Um, I spent 8 years at Alphabet working on image understanding with deep neural networks. We published some of the early architectures for image classification or object detection, and we won the ImageNet challenges. That was 11 years ago, 2014. And I used to work on Street View as well, on 3D pose estimation and 3D vision for Street View. As the vehicles used to drive around, we would reconstruct the world in 3D, align all the different trajectories of all the platforms. We even not just have cars, we had snowmobiles, trikes, bicycles. Sometimes we would put a trike on a boat. We've done all kinds of things at the time. And so you had to have accurate pose so that when you navigate for all these photos and the pancake in 3D needs to look good. Essentially, I led a small team that was enabling this for a few years. And then around 2015, I got into autonomous driving. Initially as head of 3D perception at Zoox, another reasonably prominent autonomous driving company. And I did this for 2.5 years. And then I had the opportunity to start and form this Waymo research team that I have been leading and evolving together with the team since then. And I think soon it will be 7 years at Waymo.
That's amazing. That's amazing. I think when we spoke, you guys were early days in the Phoenix market, trying to get some on the ground test experience for the vehicles. Talk a little bit about how far you've come since then.
So I think 21, we had a Waymo One service in Phoenix. I think it probably was still with the older Pacifica vehicles. And since then, a lot has happened. Just recently, maybe 2 weeks ago, we announced that we are now giving over 200,000 trips to customers in 4 major markets and 200,000 trips a week. So this spans
Fully autonomous?
Fully autonomous to paying customers, right? At reasonable scale at this point. It is a significant part of people's lives in these cities and an option that they can clearly use anytime they would like. You can get the app. You can just hail a Waymo in San Francisco, Phoenix, and LA directly. And now in Austin, in a partnership with Uber, they need to go to the Uber app to hail a vehicle. And often, or reasonably often, it would be Waymo. But in these four cities, we operate at reasonable scale in large territories too. So San Francisco, we have the full city and even a little bit of, I believe, Daly City, so around 55 square miles. In Phoenix, that's our oldest area where we provided the service and is the largest area, I think, generally in the Western world. I'm not sure in China how it goes, but Phoenix is over 300 square miles, and there we even provide rides to the airport directly. And then we have the other two cities. They're around, again, LA is maybe 90 square miles, and Austin, where we're relatively recently around 37, I believe. When we were building it, we were not sure how enthusiastically it would be received and how much people would love being in an autonomous vehicle. I can tell you that, at least for myself, and I'm a biased user, of course, because I contributed a lot of, well, systems of features to uh, that, either are part of the vehicle or help support the vehicle. Uh, I think it's an amazing experience. I think a lot of people also really appreciate the safe driving, the comfort, the fact that, there's significant amount of privacy. You're there by yourself and safety as part of the experience. You can play your own music. I think generally people that try it, a lot of them are hooked pretty quickly. And so it's validated the vision that autonomous vehicles can be compelling, they can be safe.
The company recently published some updated safety numbers. Can you talk a little bit about that?
Yeah, so we share safety studies and also safety numbers of our service as we operate in all these cities, and we update them regularly. There's a hub, that the safety dashboard on the Waymo website, where one can keep checking in. And so the most recent update was at 50 million miles. And there we share statistics about our performance as we drove people for first 50 million autonomous driven miles. Actually, every week we drive more than 1 million miles using our fleet. We drive customers. And so in this 50 million miles, there's different groups of incidents ranked in terms of severity. And so the most severe we track is, for example, incidents in which airbag was deployed. These are fairly serious, high impact incidents. And we are over 80% safer than normally human drivers would perform in our estimate, right, in the cities where we drive, in the conditions we drive, when we adjust for all of this, we find that we are, I think, 83% fewer crashes that result in airbag deployment than if humans drove these miles. And that's a non-trivial amount. So if you given the miles, that's over 60 crashes that we have potentially eliminated by having Waymos drive this. And the second category of incidents is ones where there was some kind of injury, right? And that one, we're over, again, 81% safer than an estimate of what humans drivers would, given our domain where we drive. And the third class is ones that are actually police reported. So more minor incident, but still often you can report to police. That one we're about, I think, 68 or so, 64% more, how to say, fewer than our estimate of what humans would do. So these are significant improvements. And also, separately, we've had studies done by insurance companies, third party, that also confirm that in terms of like property damage or injury claims, we are about 80% less than what humans would do for comparable amount of driving. That Swiss Re is a company. So this is another separate benchmark, not just ourselves benchmarking us, but we will continue releasing these. But it's, I mean, that's what a lot of us are in the space, not just for the experience. I mean, I think we always, many people are the joint the autonomous vehicle domain are motivated by the great safety benefits and many other benefits that these vehicles can bring to the communities that they serve. And so, but this one's the main one. There's tons of people that, I mean, safety comes first. Our mission at Waymo is be the world's most trusted driver, right? And it underpins everything we do.
Is it still the case that the vehicles are to some degree remotely operated, either on an intervention basis or otherwise? And do you publish stats around that and the number of incidents per mile or something along those lines?
I think in terms of can an operator, inspect the vehicle? I think that is possible, right? But it happens rarely. And I think the fact that we've scaled to such amounts of vehicles and such scope, you're not gonna do it if there's people watching over every vehicle, right, all the time. That's just not a good product. What did you eliminate? You moved the driver to sit behind the workstation. That doesn't work. And so this is mostly in very rare cases. And also, the vehicles, just to be clear, they're not teleoperated. So it's not like someone drives them remotely in these cases. At most, occasionally, a person can confirm something the vehicle wants to do. And usually the vehicle already needs to be stopped for this to happen.
Yeah, it seemed like that having a real time loop for that kind of confirmation would be very difficult.
Yes, and you do not want it. But then that means that you actually need to understand and deal with these issues at least to understand to stop for real, right? Which is, you know, again, very rare. That's also not even a good experience. You don't want to do it. So while it's possible, it's very rare.
So tell us a little bit about how, from a research perspective, you've been tracking and thinking about incorporating all of the ideas around foundation models, LLMs, VLMs that have sprouted up since the last time we spoke.
So yes, generally we look at the state of the art in machine learning and AI. Our team and has tried to adapt the advances to our domain, and usually it has involved some creative adaptation. So there is some unique properties of the problems we're solving. And traditionally, we had to do adjustments or fairly creative adjustments of the techniques we see, right? Now, every 2 years or so, my experience in this space, and I'm in it since 2015, actually, in December, maybe early 2016, is there's big technological leaps, and a lot of them have to do with machine learning or AI. And I think generally in this space, you want to keep reinventing your stack. So as these advances occur, you digest them. You want to be at the forefront and take the benefits. And I think what's happened in the last 2 years, if anything, there is even bigger jump than before with these multimodal large language models, with generally generative AI technology that also spans multimedia, obviously images, video, understanding, audio, handling, all of these things. It's been a bit of a revolution. And, we are keenly aware of the advances and we have been exploring them for the benefit of our driver, right? And so we've engaged in understanding and leveraging the technologies such that vision language models, right? Such as diffusion prediction for generative outputs that can include videos, but they can also include like generating driving scenes for testing. We have done. We leverage things like 3D reconstructive advances. There's a lot of very interesting new technologies,
Like
relatively
Gaussian
speaking.
splatting and that kind of thing.
Gaussian splatting, before that nerve, right? These kinds of technologies are also very interesting, and we've been working on them. But generally, right, recently there has been these trends to scale the models and train them on a lot of data, scaled architectures, um, over time add reinforcement learning, right, to target even better reasoning capabilities. All of these things, I think that's the general trend in the space, and you can see it with all the large models. Uh, we have been scaling our models for a while, and we've had um, actually transformer architectures for a while. If you see our publications, we had a few even externally published around 22, 21, with transformers even before that for certain applications in perception. And so we have been on this trend. But I think what has changed more is just the understanding how much more scale we can leverage. And so now we have gone and scaled the models and evolved them beyond what normally we used to do before. And we have seen clear benefits from doing it. Now, just one thing I want to describe is why is our domain different than a vanilla vision language model? And by the way, speaking of vision language model, we have, for example, experimented with them. We have even published a paper called Emma last year, where we took a state-of-the-art multimodal large language model, what Gemini people like to call theirs, and tried to adapt it for driving tasks. And adapted it reasonably successfully. We got some very nice results on the driving tasks with the,
And
I
this
think,
is
a
the
variant
idea
of.
of converting trajectories into tokens and passing them through the VLM.
So the way it works mostly is, okay, so what does Gemini bring to you? It brings to you world knowledge. It's pre-trained on the internet, and it's a large model. So it understands a lot of concepts already that you don't have to teach it directly with your own labels or data. And then you fine tune it on your tasks. So now you bring your own data and your own tasks, and you adapt it to do well, given all this knowledge it brought to the tasks that you fine tune it to do. And of course, you need to adjust a bunch of recipes. You need to make sure that the tasks are well represented in the Gemini inputs, and that all the sensors are properly scaled and the right data sets are created, and so on. But then when you fine tune it, right, it does a reasonable job actually on these tasks. But there are still limitations. For example, our stack relies or likes to rely on really powerful spatial awareness of everything going on around you. It's helpful for safety, but then you need to understand the world in 3D even better, right? And we have additional sensors like lidar and radar that are really superb for contributing to 3D spatial awareness that you want to incorporate, which a vanilla Gemini model does not do. Another thing you want to incorporate is very long memory over a scene. You need to reason often, based on the history of several seconds or more. That can be a lot of frames. You need to incorporate this memory, somehow maintain it, somehow structure it. You need to think how to prevent hallucinations, right? So the model can predict things, but every once in a while, if you go to domains where it has not seen things, it can be wrong. So you need to think, okay, what are the way we have actually a lot of experience, uh, you know, launching machine learning, powerful machine learning in every part of our stack, but doing it in a way with the stack design that is built to also mitigate all these issues of falling off the data manifold, hallucinating, and so on. So all of this, are still areas that are very much ripe for further work, even though we have these vision language models. But we want their power. We want to bring external knowledge, right? Internet has a lot of knowledge when you pre-train it. There's a lot of value in having these kinds of pre-trained components, and we also can benefit from some of the architectures and scales.
What are some of the specific tasks that you've explored using VLMs for?
I mean, for example, there obviously can be explored for understanding all kinds of perception outputs, right? So they understand semantics very, very well. Right? They're trained such that you show it an image, you can ask a variety of questions, and a lot of them are really powerful on all kinds of even fairly obscure details. That traditionally is a property that you want to benefit from, because otherwise, in the old days, maybe 5 to 10 years ago, you would use humans to label all these concepts. Now, that model, for example, would understand a lot of them out of the box. That's very powerful, right?
So the idea being the model sees the scene, and as opposed to the old world of bounding boxes around humans, balls, scooters, that kind of thing, the model just knows what those things are and that they're important.
Yeah, and without us having to label all these concepts, right? So you can directly bootstrap yourself. The other power of all these models is the more scaled they are, the larger they are, uh, the better they generalize. So if you see some new variant of the concepts you for some reason didn't label that you need to handle. Before you would have to label a lot of examples for the small model to really capture what those things like. And then every new particularly different looking thing, you'd need to label more examples. Here, for perception, mostly I'm thinking here as I'm describing. Now, the large models are just like, I mean, you can take Gemini or a lot of these other external vision language models. They mostly would understand what it is already, and it's a big model, and it generalizes again. It can, when it sees a trench, it can see a trench in a whole bunch of conditions and know it's a trench. For the small models, this is harder. It requires more bespoke engineering to ensure, and so that's a nice benefit, right? Now, uh, the scaling part uh, is appealing, but there's also this interesting uh, limit. There's this question: how far can you push scaling, and how much of this knowledge can you bring in our models, such that now we can get data from new cities, from new countries, from different software platforms? You can move the cameras, you can change the lidars on the vehicle over time, right? Which we do. We have a 6th generation driver that keeps evolving the sensor stack, which is then it's something to think about. So when you have all these properties, the question is, can we have a model that just generalizes across all of these things? We want to scale to dozens of cities. We want to do that much bespoke work. And the best way to scale a model is, let's try to scale it in the data center first. So remove constraints of real-time response, which needed to be for safe driving. Remove the constraints, even potentially to only see events as they unfold. You can see potentially how in the future. Remove constraints on how much you can scale the model. Now, how much understanding can you get out of this model? How much can you generalize? And so we have been pushing to understand this question, and I think we have been aiming to build what we call this Waymo Foundation Model, which is not just a vanilla VLM adaptation, but we want to bring in all these capabilities I recently talked about that expand on a standard vision language model, and build it large, build it in the data center, and see how much can you just understand all the data that we see and we collect. And the better this does, the more straightforward it is. Then this model then acts as a teacher to the models in the
To
car.
distill it down to
Yeah, you
the
can
vehicle.
distill it down, and of course, you still need to do this with a thoughtful design, ensuring that the onboard stack fits all the safety constraints, all the latency constraints, and so on. But then this thing is just the source of knowledge that you can always ask, and both to mine data, to understand data you mined. And there's a very interesting question: how far you can push it? But the more you push it, the more you accelerate the scaling or seamless scaling of the service, right? So we want to explore that. I think that's a very exciting direction, and it's in tune with the time today, right? I think it's the age of these types of models.
And it tackles one of the historically, challenging aspects of autonomous vehicles, and that is that generalizability. Like the vehicle, you've got lots of data captured about a particular road during the day in clear weather, but the vehicle needs to operate in that same road at night in bad weather. Historically, you'd either need to capture that data manually or use some kind of data augmentation scheme to train the model so that it can adapt to those variations. But if you're able to achieve sufficient generalization with a scaled up model, that eliminates, I would think, a lot of the challenges of getting coverage in the markets you're in, and getting into new markets?
So the reality is we have good generalization and coverage in the existing markets already, right? And we operate on them clearly and have passed a certain bar. But new market, and the more different the new market is, or the more different the new market and sensor stack is, the more it pushes your ability. And then, you can do it a lot faster if you have this kind of capability than the process today, which would, of course, involve you would go explore the market, collect data, label some data, understand anything that may be different, make sure you're confident that you're safe, right? Like there is a standard procedure how we ensure safety in the market, I think, which is important, but we could accelerate it.
How long do you typically need to be testing and collecting data in a new market in order to launch in that market?
I think it's been a very much evolving process, meaning the first time, say, we did Phoenix, we did East Chandler first, which is a bit of a suburban area of Phoenix. And suburban areas have one set of challenges. For example, unprotected left turns on the freeway, or not a freeway, but a reasonably high speed road, 45 miles an hour, and then people speed, so it can be a lot higher. And it's really important how you can go in front of traffic going at such speed. And there's a few other challenges there, but it took a while to sort out, right, and make sure our system is robust. Then you go to San Francisco and you see, oh, it's totally different. There's all these crowds and totally different behavior, and the streets, big part of the city, are a lot narrower, right? And it's just different, dense urban scenario. So there it took a while too. And then we go to Los Angeles, which somewhat combines the properties of the suburban Phoenix, and by then we had moved more to downtown Phoenix and so on. So we had a bit more of a span, everything from a bit more suburban to urban to dense urban. And you have San Francisco. So when you combine those two, LA actually was fairly straightforward, right? So as we cover, it's about a bit of covering the design domain. The more you cover it, right, through, and in our path, we've been doing this, the easier it is for the next city. They generalize. So every new part you collected helps you with the next part. So it's an accelerating process too. Now, separately, what do we work on a lot today? Freeways. Freeways offers a whole set of new challenges compared to the ones we've seen in, say, the more suburban areas or dense urban. There's different things to be concerned about, right? And you need to validate. For example, on freeway, you need to be robust at 70 miles per hour or 65 miles per hour to any kinds of failures that can occur. And also, you need to worry about, stopping at any position on the freeway that's inherently unsafe, right? And sometimes there's not even shoulder for certain parts of freeway. So you need to think, what do you do there? And that's a different bespoke work you need to think about. And another one, of course, would be snow, ice. That brings yet another dimension. There's a few of these. So I would say I can't tell you an exact estimate because it really varies. But we have a robust process to ensure that we gain sufficient confidence in the market before we launch.
In the markets that you're in now, do the vehicles operate on freeways, or are they only on surface roads?
So for most customers today, we do not provide freeway, fully driverless on freeway, but we are testing on freeway for a while actually without driver in some capacity. So it's still an area which we're scaling and working on. And so we, of course, would very much like to provide this to our customers, but it's still an ongoing process, right? For example, take Phoenix. We're clearly motivated to the freeway because Phoenix, for example, is 300 square miles. Going from one end of that area to the other, you really want to take the freeway. Otherwise, the service would, uh, take a while compared to what is possible. You want to provide good service. So it's clearly an area of high importance.
So, kind of going back to the foundation model work, when you think about this challenge of scaling up the foundation model in the data center, one of the uh, challenges that you mentioned is incorporating all of the different sensor data that you might want to incorporate that aren't necessarily native to VLMs and to images. How do you approach that problem?
So it's a very interesting problem, actually. It's a bit open-ended how to do it best, right? And I think maybe um, one way to think about it is also audio is an example of this too, right? So initially, when you do a model, you people tried images first, and then later the audio became a domain too. So you want to build a multimodal model. Now, how to actually build it and how to insert data from a new sensor into a model that was trained potentially, or pieces of the model that were trained without it, it's actually an interesting research problem, and there are many approaches. So I can't tell you how exactly we do it. We're experimenting with several and learning along the way, but we find that it's one of the key questions in our domain how to do that.
Is building a foundation model on top of existing VLMs, like the part of the motivation for that is taking advantage of the world knowledge that is embedded in that. But the alternative might be incorporating, I'm sorry, training from the ground up a foundation model that understands these different modalities and is able to do the things that you want to do.
So you can
It's
train it
not clear
ground
what
up,
exactly
right?
that would look like either.
So, well, exactly. Well, there's this interesting question of, okay, so let's say you train something fully from scratch yourself, but then you need to worry, well, how do I bring all this knowledge that people already usually put into this from the internet, right? So you still want to somehow, then maybe you need to get that
There's
data,
still some kind of
right?
fusion of modalities that needs to come together. It's just a different way of looking at the problem.
Right. And so there's another thing though we can do, which is we right, and it's also expensive, of course, to train a model fully from scratch, right? So you need to think that's one aspect of things. The other aspect is, okay, how can we learn and build a model from our domain, right? Using data from our domain directly, separate from the fact, okay, well, one is you leverage hopefully world knowledge from models one way or the other, right? You need to think how. Maybe you can even use them to label data for you, or you can take pieces of them. There's many things possible. Now the question is, how do I train model in our domain to understand our sensors, right? And there's this interesting question. You can learn in our domain to predict the future also, right? So how do you pre-train large language models? You predict the next token in language. What can you do in our domain, right? You can do things like you can predict what the sensors give you in the future. So imagine if you could to tokenize your sensors, you can predict the next sensor token and the next sensor token. And if a model is able to predict accurately how sensors look in the future, whether it's lidar or camera or radar, then it will learn a lot about the environment, because uh, it will actually capture all the knowledge inherent to predict how things evolve. So you can imagine how you will see them. And that's very powerful pre-training. This is equivalent to this kind of pre-training next word prediction. The issue is only, of course, a word can be tokenized in maybe 100,000 tokens or something to that effect, and then you're predicting a distribution over 100,000 discrete tokens. That's fairly straightforward. Now, our sensors, they're high resolution. They're different multimodal. Now the question is, well, for those
The
sensors,
vocabulary is a lot
what's the
broader.
vocabulary, right? And
Right.
how do you tractably predict it? And that opens a whole bunch of interesting questions, right? And it's a question: do you need autoregressive models? Do you need diffusion type predictors? How do you set it up, or a mixture of those? What is effective? There's work in the space already in academia trying to build these, and in the industry already trying to build it's called world model. You're dreaming the futures in the world that you're modeling, right, from your own sensors, and that can be useful to also train large models, right? But how to best build it is also a very fascinating question. And of course, the richer futures you dream, the larger models you need, because now you need to capture a lot of the nuance beyond a certain level of, oh, can I scale some model to just predict what I should do and maybe more some high level properties of that is, versus predict everything in super high pixel lidar scan level fidelity, right? You need potentially larger models to do that well. And so there's trade-offs, like how much of the compute now you're going to spend to pre-train these very large models, how much of that actually results in driving improvements, say, for you in the end? And how does the math work out? Is it compelling enough? This is also a very interesting question. But for good or bad, some of these world models are needed for the simulator. So you need to think how to build them regardless, right? We want to. So in our domain, it's not just about building the driver. There's two main problems. One is build a driver, right? And I talked to this also about this in my GTC talk. The other problem, which
And
is
you got
by
to
no means
validate the
easier, is to
driver.
validate it and ensure that
Right.
you are confident this model or driver perform well in the vast majority of cases we need to handle, right? Like the environments in which vehicles drive span all kinds of diversity in season, as we already talked about, different operational domains. There is all kinds of human behaviors, some of them very rarely seen, that you need to deal with in front of you. You need to interact with humans. So all of this, of course, is great to test in a simulator and is a great tool to test at scale. But now the question is, how do you build this simulator? And now you want to use machine learning to build it, right? And
Before we dive into validation, I want to dig into this idea of like predicting future sensor values. When I think about that, I think that there's like a causal relationship between the vehicle trajectory or the vehicle behavior and then what the sensors, pick up as the vehicle progresses through, a scene. Um, and I'm trying to kind of wrap my head around like what it means to predict future sensor values as opposed to predicting the thing that is like the root cause of that, the vehicle trajectory. How do you think about the relationships between future sensor prediction and like the vehicle itself and what you using that as a control input or something?
so I just contrast the two a little bit and see if we're thinking of the same setup. So in our EMA paper, for example, right, you have a vision language model. And one of the tasks we can teach it to do, even though we tried several, like you can predict the road graph that's in front of you, you can predict the 3D boxes that you see. But one of the interesting properties, the main one maybe you predict, is what's the driving trajectory you're likely to follow. And you can, of course, sample several. And the start of that trajectory, actually, then you can turn in the controls. The rest is more speculative, kind of showing you what it's likely to be like over time, right? And of course, the longer you predict a trajectory, by the way, in our domain, it's the more uncertain it gets whether you're actually taking it, because it also depends on certain assumption of the world
Kind of
around
like
you,
next
right?
word
So
prediction or next
yeah,
token prediction.
but like, I can think I'm driving this trajectory for 8 seconds, but if the vehicle in front of me swerves, I'll adjust it. So it's all relative to what the others do a little bit as well. That said, it's a very good output, and the start of it you always would drive, right? So it's related to planning quite strongly. But the trajectory, how do you train this model, right? In our domain, you would actually observe either our drivers or potentially how others drive, and you saw what they did in the future, and you collected it, and now you're teaching the model to predict just those tokens of how driving tokens for a few steps in the future. That's a signal, right? That's the most topical signal for how you should drive. You watch how people drive, you see their tokens, and you learn to predict them. Now, when you think of sensors, it's it's essentially the environment that goes with how you drove. So instead of predicting just how you drove, now, for example, maybe a next level, imagine is I observe others and predict how they drive next to you. A lot of the models do this already, right? So not just predicting yourself. We have a model called Motion LM published maybe 2 years ago, and it's in even all the work showing how to turn motion into conversation. And you can train the models with that level of abstraction. So you say, oh, I'm not just teaching our model to predict how I drove. I'm going to teach it also to predict the other people's motion tokens around us. And so you predict jointly how a whole group of them now behave. So that's a richer signal. You're teaching the model more things from every one example. And they're highly topical. Now you're teaching it, oh, not only how I behaved, but how everyone else reacts to me, and then maybe how I would react to them. You're modeling what we call the joint distribution of at least some group of agents around us. So that's a richer signal. Now imagine you go to sensors. That's maybe very high bandwidth, detailed variant of everything that happened before. You not only see the environment not only changes because you say did certain driving paths. It also changes because others reacted to you and changed their behavior relative to you. That's also reflected in the sensors. And beyond that, you need to think how everything actually changes appearance as you and how objects may look from the other side if you surround them, and how reflections may work, and how certain lidar intensity relates to the RGB pixels. Because now you're dreaming the future of the environment, the full environment in its full fidelity. So they're
There's
all
an argument that it's like a more grounded prediction and that it's reflecting the actual environment that the sensors are intended to
it's
see.
the most high bandwidth prediction you have. This is all the
Mm-hmm.
information you actually had about the future, which is your full
Yeah.
sensors. And that's the most you could try to predict. But then the issue is, are you overdoing it? Like, so for example, humans, I don't spend my time thinking how the tree looks from the other side when I drive, right?
Right, right, right.
Or like, as I go, how would the branches occlude each other from a different viewpoint? Or how the shadow will evolve on that pedestrian? I don't necessarily have to think about it. So while there's a lot of knowledge inherent that the model can capture, not all of it is relevant to driving. Some of it is. And so now there's this interesting trade-off. Do you really want to go all the way there? How much benefit you're gonna get? Or do you do something? Clearly, some version of fidelity is relevant. So like predicting what people did a few steps in the future is the minimum you can do and the most topical. And then you broaden and it becomes uh increasingly less relevant. Like, you want to model how the clouds move in the sky. Maybe it's relevant to it raining in an hour, but I'm not sure it will help your driving soon. So there's this trade-off. There's a ton of signal in these sensors, but you could choose to model it. It's helpful in some cases for a simulator to model it, but it doesn't always help driving. And so we're discovering what is the right recipe.
Remind me, or maybe talk a little bit about the way your approach to kind of end-to-end training versus subsystems that maybe map to traditional approaches to uh, robotics or vehicles. Like, are there separate control, perception, et cetera, systems, or are you moving towards or away from end-to-end modeling? I vaguely remember us talking about this a few years ago as one of the um, uh, kind of differentiators of your approach, but I don't remember which side of that divide, if you want to
We're
call it
we're
that.
on the
You
practical side. We will take the thing that works best, right? I think that's what I would say. Now, there is end to end in general is a bit of an overloaded topic. I know it's been made into a big issue by a lot of people. It's compelling in some embodiment, right? But let's untangle what end to end means, right? So end to end is a if you think there's kind of mild definition and a strong definition. So end to end means typically, right? The strong definition is, hey, you're gonna pass some gradients from, sensors, from controls, what you want something to do, through a whole system, maybe to the sensors, and you'll along the way learn features that you may not necessarily be able to inspect yourself or that have semantic meaning that just emerge from the training process that may help you drive, right? End to end in general is a training strategy. It's orthogonal from whether you have modules in the stack, right? You can still have modules and train things end to end, right? If the models are connected properly and you can pass gradients between them, you can, right? And you can still train many tasks end to end. So it doesn't have to be sensors to control, right? You can even potentially consolidate large pieces of the stack. So every piece of your stack became more end-to-end because initially, say, you had bespoke 10 different models handling certain tasks, and now you consolidated them. That part became more end-to-end, all right? Now, so it's a complex topic. Now, I would say that what we've learned over time is that you want few large components if possible. It simplifies the development, right? It allows you to essentially scale those components more and optimize them as opposed to have a bunch of little custom things, each doing different stuff with different data generation. So you want few consolidated components. And now the question is how few. And of course, the other part to know is if you have a few, you still want to ideally backpropagate through them. But how few, and can you just make do with sensors to controls, the extreme? And the sensors to controls, I think, is what people are really excited about in academia. And it's very powerful in an academic setting.
And it's a compelling idea. Just collect enough data. You've got some black box in the middle that's sufficiently, has the sufficient, scale or number of parameters, and you've got some desired output, and you let the middle part figure it out.
And our EMA paper does this too, right? So we do train it end to end clearly, right? And predicts nice trajectories and generally does a good job with a fairly straightforward recipe. So that's appealing. But the big questions there is, uh, can you simulate and prove that this system does not hallucinate, does not
Provability, controllability,
testability?
introspection,
Yeah. So how do you
testability.
validate the system? Now I need a simulator that's, uh, always from sensors to controls. And in our domain, there's quite a lot of sensors, and they're not that easy to simulate. The technology for this has been evolving. And then you're really tied to this. You need to scale it. You want to see, imagine driving over 1,000,000 miles a day in the simulator and now having to simulate everything you could possibly see in these sensors. And usually most companies have at least a couple sensors, different ones. And you need to, at 1,000,000 miles with over a dozen cameras, with a few lidar, for example, or radar, right? And it needs to be really realistic. Otherwise, it doesn't count. How do you do it, right? That is the challenge. How do you prove to yourself now that all these cases can be validated just with this setup? That's hard, right? And so there's push and pull. Also, the other big questions. Let's say you train a huge model, and now you want to change it. Well, what do you do? The only thing you can do is you change the data to it or you train the model. Now you fixed it, but maybe it broke something else. How do you? It's really hard to fix something really quickly if all you have is a model that goes end to end. So there are all these considerations. So I would say that there is consensus, reasonable consensus in our space that you need few large components, but there is no consensus yet if it should be one component. And I think a lot of it comes from testability. And so if you want to say, in our case, when we're doing actually fully autonomous driving, it's top of mind. You design your stack in a way that you're sure you can test. So that's a constraint. Right. So we need to, anything we do, we're doing with the mindset that, hey, we actually know how to test this at scale to actually deploy a driver. When you're doing driver assist, it's less demanding. You don't have to test it to this extent. So maybe there you you can get by with a fully end-to-end model, as some people have. But in autonomous driving, when you have to release it there to drive, hundreds of thousands of trips and millions of miles a week, that's a high bar, right? Between that and ability to fix things that arise, these are top of mind when you build a stack, when it's fully end to end. So you need to have an answer, I think. So these are the trade-offs, and we're doing our best thing. I think it's appealing to do end to end generally. It learns good features when you can do it. Just prove to yourself you can validate.
Does the more modular approach that you've taken give you um, the controllability, testability, introspection, quote unquote, for free, or are those all active research topics as well, like how to um, how to ensure a degree of, I guess explainability was the word that was briefly escaping me.
Explainability and controllability. You want, if you have a model and it's some big VLM, even or whatever, like we did with Emma, you want to have a way to detect and steer it when it's doing wrong things and it's hallucinating. So you need a harness around it. There's two kinds of harness you can have. You can build a harness around it that operates in the system you deployed, that makes sure with, there's ways to do this. We have experience. You can make sure to catch this model when it hallucinates things that it should not do and control it on top. The other part is you can catch it in the simulator, the other part we discussed, right? But then you need to build a fully realistic simulator. And in both cases, you need to understand the world a lot deeper and more symbolically than just having sensors to controls. I would say that.
And you need to somehow get the confidence that you've run sufficient simulation samples in order to get the coverage you need to.
Oh, that's what's called science. Actually, it's extremely hard. And I think there's this other interesting aspect of the simulator is, so for example, as you collect more data and make your model larger, you can have it to predict better trajectories for you. So it's very uh, efficient in some way, data efficient to, if you just want to improve over time and you get more data, you can keep adding data and the model will improve in certain ways, at least over time. In general, right? Uh, when you want to test it, you cannot do that. Like you actually need to think about the cases that could go wrong. You need to create some ways to validate all of those. They can require all kinds of hardware failures, sensors going wrong, rare cases, you name it. You need to somehow handle all of this in your release cycle. That does not work as well. Like you just take data and you just feed it in the simulator and the simulator tests you better. It's also true, but it's not sufficient. So you need to be very thoughtful on the testing side. It's not purely a data driven exercise. You need experts thinking what could go wrong and working on mitigating that. And it scales less straightforward than something where you can just put data in and driver would improve with more and better data suitably picked. That is true. But your ability to test it is not similarly scalable.
How do you characterize the test coverage or the testedness of a given model? Do you need to get to approvably, some standard of, proved valid, or is there more of a statistical determination of testedness?
So, like, I think you need to be very comprehensive. And that's why it's hard to do just, it's not just some data driven model that you just do throw data in and it somehow tests you.
But you're also not trying to get to like NASA levels of mathematical proof of, complete controllability. Or are you? I
I
guess
mean,
is the
there's also
question.
this question, how do you even prove it, right? Because if people do very unreasonable things, some of them you cannot even mitigate, right? Like you're stopping and someone tailgates you at full speed. What are you going to do? You can't even get out, right? Uh, so it's all relative to what's reasonable to expect. But I guess if we have published our safety framework, we're one of the fewer companies that have done it, and that details the whole set of tests we subject our driver to when we want to release it, and it's a very broad set, and it includes both of kinds of hardware testing and failure injection and all kinds of standard analysis techniques, and it includes simulator, and it includes driving in closed courses and testing with drivers and all kinds of things, right? Like uh, we this actually difficult to develop. It's very comprehensive. It takes a lot of effort, but Waymo's shown that we can iterate over time and release improvements to our stack uh, while going through this validation cycle. And I think that's one of our great things that we've been able to accomplish is to have that, right? That said, it's bespoke, it's diverse, many things are combined. But if you ask me, what are we testing for? You need to test for a lot of things. One obvious one is you should feel you can be safer than the human. driver. And right, that's one. Second one is you should be confident you don't get stuck all over the place either. The third one is okay, you don't want to, you want to be thoughtful and mindful around, say, ambulances and police vehicles. It goes on and on and on. The amount of things you need to be able to do is broad. You need to, in construction, for example, or if directed by an official with some gesture, you need to try to understand it. It's a broad set of cases you need to check that you can handle.
And going back to the question about data only and end to end versus, you know, we didn't explicitly talk about like a rules based. Like how do you in, incorporate that long list of scenarios into the model in a just throwing more examples into a data set isn't good enough. Like how do you do it?
And there's different ways, right? I think generally we have a lot of experts, right, as well, into what is good driving, motion planning experts. That's one. Second is there's generally this question of how do you define a reward function for driving, right? So what's good driving even? How do you define it? How do you ensure your stack satisfies it? It's a very interesting question. I mean, so far we discussed maybe imitating some drivers. That's one way to define it, but that's not the only way. You can say you should not do a whole bunch of things. So you can read this rule book and ensure that certain things are true and optimize for it, right? But I think it's a difficult endeavor um, to define it and then make sure the model uh, take that into account. It's an evolving space. We have reasonable approaches. I think generally, as you can see, some things are easier to define than others. For example, don't hit things is somewhat straightforward.
Now I'm thinking of like just yesterday. I was on a road and there was some work happening to transformer on the side of the road. So they combined the 2-lane highway into 1 lane, and they had signal people on each side with either the slow sign or the stops, the sign that spins from slow to stop. Like, and I'm thinking about in the context of this conversation, like, is that something that you just get enough data about those situations and the car figures out what to do? Or do you have some rule set somewhere that, kind of defines for the car, like when this is happening, like this is what's going on and this is how you're to behave? Or does it follow more readily from what the car in front of you is doing than I might think? Like,
It's complicated because a lot of those things as well normally shouldn't cross say the lane boundaries. But when they put the cones, they actually should. But then separate from the cones and the sign, the human actually gestures you to do something, right? These are that's what makes it very complicated.
yeah,
Yeah. So we combine different approaches to make sure we can handle this as well as we can.
it seems like an example of at least a failing of uh, a fully end to end process. You need to collect a lot of data about a lot of, what are probably unique, individually unique situations that have this pattern in order for the vehicle to, on its own, do the right thing all the time.
And it's limiting. One thing that, so if you did not see some situation, right, the model may just nail it or it may not, right? And that's a challenge. Now you need to know, does it nail it often enough where you say it's good enough, or does it fail often enough where now you need to think of other things to do? Um, that's part of the, convincing yourself, validating the driver story.
You mentioned earlier, we talked about NERFs and 3D Gaussian splatting and diffusion models. You mentioned those as technologies that you were looking into, and a lot of that comes up in the validation part of the equation. Can you talk about some of the ways you're using those technologies?
So I can say the following. I mean, so far I was trying to tell you, hey, validation is difficult to scale. It's complicated. You need to, handle all kinds of eventualities, and some of them need experts. It's true. But the best way, or one of the best ways to scale validation is still to use machine learning to build the simulator better, right? And because simulator is one big part of your validation story. And now you need realistic scenarios and interesting scenarios to be played in this simulator. And traditionally, maybe 10 years ago when I started, the state of the art in simulation was computer graphics methods. So you collect a whole bunch of assets, houses and trees and, whatever, and bollards. And then when you drove it, you understand those assets, where they are and how they look. And then you just replace it with the assets. You place them there, ideally automatically. And then you have a world. You have a 3D world. Now you can drive in that 3D world and you can use computer graphic technology to make it look
But even
realistic.
then, there was a sim to real issue where the models wouldn't react to the graphical versions of the things in the same way that they'd react to the real world versions of the things.
It can easily be. And this is still true in a lot of robotics. Now, it's true that they're correlated, right? They look similar-ish, but they're not the same. Uh, and so, why? Because, I mean, honestly, computer graphics, again, is certain approximation and who set the properties of the, what should the sun be like and what is the diffusion aspects of the environment and is there fog? Like, you need to set a whole bunch of knobs properly. What is the camera, you know, detailed? Is it grimy or not? And you need to somehow needs to model all of this. It's really hard in a computer graphics environment. There's a lot of knobs, even though it's nominally powerful. Right. And so then there is this gap. And also, how good are you at taking what you drove and place all these assets? Did you have all the assets? Did you not have them? If you place different assets, if you set the conditions differently, is that again, the gap is there. So you're not guaranteed that you will be able to well reconstruct anything you drove. You can drive at night in the fog, in the rain, and things may look different. Now, the dream from scalable simulator is to be able to just reconstruct it from your own sensors. We have enough sensors, they're extremely rich, they're cameras and 3D sensors. You should be able to go a long way into just building yourself the simulator from what you drove. And so the dream is, right, and that's something we work to enable, is any situation I drove with my car, I can build a simulation environment from. I may have to populate it with additional traffic suitably. That's where generative AI comes in. I may need to evolve it in response to the things I do because my decisions impact the decisions of others. They respond. I need to model that correctly. Otherwise, you're not going to have realistic outcomes. If the agent drove like what it drove when you weren't in front of it, it will plow into you just because you did it naively. You can't just replay what the agents did naively and get all the signal you wanted. So you need intelligent agents too. So between reconstructing the world and being able to drive, say, this intersection in San Francisco, I want to be confident I can drive, and being able to populate it with agents that behave like I is reasonable for pedestrians and vehicles to behave. That's a really interesting, challenging machine learning problem. And so I'm inspired by it. It's fascinating. I think some of these technologies, 3D Gaussian splats, diffusion modeling, on the there's a 3D Gaussian splats and nerf for the reconstructive side of things. So you can reconstruct really well a representation of the environment you draw, but you can't, those technologies don't necessarily allow you to augment it or dream it or turn day into night or place new agents so easily as it would be now, for example, something like a diffusion model. So that's more of a generative type of model. You can dream new parts of the environment or agent behaviors, a complex one where the appearance matters or futures. But, again, do you dream freeform or do you want to condition yourself and land yourself at some specific intersection in San Francisco? How do you do the two together? There's some interesting questions here that I think the field is now making progress on, so it's exciting, and we are alongside the field as well, making some, I think, exciting progress.
One of the ways that you make some of this progress is by offering challenges to the broader community to help you solve some of the things you're focusing on in a given year. And you recently announced those challenges for 2025. Can you talk a little bit about those?
Thank you for mentioning this. We've been engaged with the academic community since 2018. We started working on this when I joined Waymo. In 2019, we released Dataset, at the time the largest, most comprehensive we had in terms of actually having high quality Waymo sensors and quite a few scenarios compared to what was reasonable for the time. And we kept upgrading it every year, adding more and more either tasks or potentially additional examples of interesting driving or things that need to be understood. And in parallel with dataset work, we organize challenges on tasks which we believe are exciting, and there's headroom to make more progress in terms of interesting approaches and solutions. And so this is our sixth year. We actually have not announced them yet. We probably will announce them by the time this podcast airs. They're supposed to launch in end of March. And every year we do 4 challenges. So we pick certain tasks. We've done over 15 so far, over 6 years. This is our 6th year. We have some very exciting ones. So one of the interesting ones that we're aiming to launch that relates to our conversation today a bit is end-to-end driving from just camera inputs. We are sharing some very interesting scenarios among the ones Waymo has seen. And we want to see how people can take some of these large models and get them to generalize on reasonably rare conditions. So that's exciting. We also have a simulated agents challenge. We're unique in running such a challenge. It's a very interesting problem where you're building agent models that populate the simulator, and we have ways to validate whether they're good models. And we have improved the metrics a bit this year. We have one on traffic generation, again, something we discussed. So let's say I give you the road graph of an intersection. I want you to potentially populate it with realistic traffic that, the relevant positions, velocities, behaviors are reasonable and not ad hoc, but we have ways to measure how realistic a traffic scenario is, and we want to see what people can do. And there's interaction modeling as well. That's a challenge we're bringing back with a bit improved metrics from, I think, maybe 4 years ago is when we ran it, when we last talked. So we're bringing that one back. And here I am back on your podcast also 4 years later. That's an exciting one. Modeling how agents react vis-a-vis one another well is an interesting challenge. And I think a lot has changed. So I'm excited to see how the new crop of methods that people try would do on it.
Well, we will include a link to those in the show notes, as well as a link to the past conversation if anyone wants to go back to that one. But thanks for taking some time to chat with us about what you are up to there and how you're approaching, this new world of foundation models. Very cool stuff.
Thank you so much for having me on. It's always a pleasure. And I look forward to you trying us and telling me how it goes as well when you are in the city with the Waymo driver.
For sure. Thanks so much, Drago.
Thank you. Bye.